Change one thing about a recursive function, make it call itself twice instead of once, and everything changes. Computing the sixth Fibonacci number, whose answer is just 8, triggers 15 separate function calls. In this video, we build recursive Fibonacci in Python and trace exactly where all that work goes. Last lecture introduced recursion and established a few fundamental ideas that today's material builds on. Today splits into two halves. The first half reviews recursion on numerical examples. The second half is the main event, recursion on non-numerics, specifically recursion on lists, using techniques that carry over to every other sequence type, strings included. We begin the review by writing a recursive function for a famous sequence, Fibonacci. The Fibonacci sequence turns up all over nature. One classic application models the breeding of rabbits. Here we care only about the sequence itself. It starts from two basic values. Fibonacci of 1 is 1 and the Fibonacci of 2 is 1. Everything after that comes from a single rule. Fibonacci of n equals Fibonacci of n minus 1 plus Fibonacci of n minus 2. In mathematical terms, that gives us exactly two base cases and one recursive step, and that structure is all we need to define the entire sequence. Watch the rule generate the sequence. Fibonacci of 3 is Fibonacci of 2 plus Fibonacci of 1. 1 plus 1, which is 2. Fibonacci of 4 is 2 plus 1, which is 3. Fibonacci of 5 is 3 plus 2, which is 5. Fibonacci of 6 is 5 plus 3, which is 8. And the Fibonacci of 7 is 8 plus 5, which is 13. That is the sequence we all know. 1, 1, 2, 3, 5, 8, 13. Each new term is just the sum of the two before it. And notice that computing any term sends you back to two earlier terms. Keep that in mind. It is about to matter a great deal. Translating the definition into Python is nearly line for line. We define fib recur of n if n is equal to 1 or n is equal to 2. We return 1 right off the bat. No calls to make, nothing to invoke. Those are our two base cases. Otherwise, we hit the recursive step. We return fib recur of n minus 1 plus fib recur of n minus 2, exactly what the mathematical definition told us to write. And here is what makes this function different from everything we wrote last lecture. Last lecture, every recursive step contained just one call to the function itself. We returned some variation of that call with something tacked on, like adding a value. Here, the function calls itself twice in a single return statement. That one difference has real consequences, and to see them, we need to trace what happens when we run this. Picture the shape of the computation. With one recursive call per step, the calls form a chain. Each call spawns exactly one more, straight down to the base case, then values climb straight back up. With two recursive calls per step, each call above the base cases spawns two more. The computation is not a chain anymore. It is a tree, branching wider as it goes, until the branches bottom out at base cases. And no call can add anything until both of its own branches have been explored all the way down to base cases. Let us watch that unfold for Fibonacci of 6. Let us calculate Fibonacci of 6, writing each call as just the function name and the argument it was called with. Here is the big idea from last lecture. You trace through a call exactly as you normally would. But the moment you hit another function call, you must go explore that call first, completely, before anything else can happen. Fibonacci of 6 does not match either base case, so it enters the recursive step. It must return fib recur of 5 plus fib recur of 4. It starts on Fibonacci of 5, and it cannot touch Fibonacci of 4 yet because Fibonacci of 5 is a function call. And the Fibonacci of 6 cannot add anything until it knows what that call returns. So Fibonacci of 5 opens as an entirely new environment, a fresh call with n equal to 5, completely separate from the original call. Fibonacci of 5 enters its own recursive step. It needs Fibonacci of 4 and it pauses right there. It must know Fibonacci of 4 before it can even look at its other half, Fibonacci of 3. Fibonacci of 4 opens yet another environment and heads into its own recursive step. Fibonacci of 3 plus something, and we cannot know the something yet, because Fibonacci of 3 has to be explored first. Look at where we stand. 4 function calls deep, and no visible work has been done. No values are being passed back. All we are doing is exploring this path downward until we hit a base case, and hitting one is what kicks off the conquer step, where values finally start flowing back up the chain. Fibonacci of 3 calls, Fibonacci of 2, and at last, a base case. Fibonacci of 2 returns 1 immediately. It makes no further calls. Fibonacci of 3 now has its first half, and it adds it to Fibonacci of 1, that is 3 minus 2, another base case, which also returns 1 immediately. 1 plus 1 is 2, so Fibonacci of 3 returns 2 up the chain. Now Fibonacci of 4 has its first half. Fibonacci of 3 came out to 2. It still needs Fibonacci of 2, 4 minus 2, so it explores that path. Base case, 1 immediately. 2 plus 1 is 3, and Fibonacci of 4 passes 3 up the chain. That gives Fibonacci of 5 its first half. It knows Fibonacci of 4 is 3, but it is still halted. It needs Fibonacci of 3. So a brand new Fibonacci of 3 fires off its own pair of calls, Fibonacci of 2 and the Fibonacci of 1, both base cases, both returning 1 immediately, and it comes out to 2 again. Fibonacci of 5 now knows both halves. 3 plus 2 is 5, and now Fibonacci of 6 has half of what it needs, but only half. It still has to figure out Fibonacci of 4, and the exploration works exactly as before. Fibonacci of 4 needs Fibonacci of 3 first, that Fibonacci of 3 calls, Fibonacci of 2 and the Fibonacci of 1 and passes 2 back up. Fibonacci of 4 adds its own Fibonacci of 2, gets 3 and passes 3 up. Finally, Fibonacci of 6 has both halves. Fibonacci of 5 gave 5. Fibonacci of 4 gave 3. 5 plus 3 is 8. Fibonacci of 6 returns 8. Step back and look at the whole tree. This is a wildly inefficient algorithm. There is a lot of motion, but almost no work gets done until the very end, when we finally reach a pile of base cases and can start assembling the result on the way back up. And there is a deeper problem: duplication. On the way down the left side, we worked out Fibonacci of 3 and the Fibonacci of 4. Then, exploring the right half, we recalculated both from scratch. The entire branch under the second Fibonacci of 4 is a copy of a branch we already computed. Count it up. Fibonacci of 4 is computed twice, Fibonacci of 3 3 times, and 1 call to Fibonacci of 6 calls, 15 calls in total, to produce the single number 8. The same work is done over and over. 3 things to carry forward. Fibonacci needs 2 base cases. Fibonacci of 1 and the Fibonacci of 2 both equal 1, because its recursive step reaches back 2 terms, and the definition translates line for line into code. When a recursive step makes 2 calls, each call must be fully resolved before the other begins, so the call tree descends all the way to base cases before a single value returns, and the naive version recomputes whole branches, the same work over and over. Next, recursion moves beyond numbers to lists. To practice what you just learned, this course has free exercises and AI graded feedback on ludium.ai. The link is in the description.